Hi, I'm Radhika, and I'm going to be presenting to you Gestalt, Fast Unified for Localization for Network Systems. This is joint work with my mentors from Microsoft Research, Ratul, Mahajan, and George Varghese, and my advisor, Amin Vahdat from UCSD. This was work done when I was a grad student at UCSD. We first started looking into fault localization when we were asked to localize faults in Lync. Lync is an enterprise communication system. It serves more than 40,000 users in Microsoft spread across the world. It's a globally distributed system. It has a lot of components. It provides services such as instant messaging, video, voice calls, video conferencing, and such. Lync already had monitoring infrastructure. It captured call transactions, components that were used in the call, but we needed a fast fault localization algorithm to diagnose call failures. We wanted to be able to tell which component failures led to call failures. Wow. I hope you factor this in my 17 minutes. Oh my God. Okay. Maybe I should start again. All right. All right. I need to diagnose this. Anyway, we needed to build an automated fault localization system because manual diagnosis in Lync took very long. So I've shown you 6 failures here, and they took between hours and days to diagnose because the number of components in Lync is really huge, and it is a complex system. And so the first thought that we got was, let's try out the existing fault localization systems. We chose 3, Score, Pinpoint, and Sherlock, because they are very different, and they have been known to work with real systems. So we chose this to diagnose real Lync failures seen over a period of 1.5 months. And we compared their performance along 2 dimensions. One was the diagnostic time that you see along the x-axis, and the other is the diagnostic rank. Now, the diagnostic rank is the percentage of components that each algorithm deemed to be more likely culprit than the actual failures themselves. So, for example, Score had a median diagnostic rank of 100. What does that mean? So, Score thought all of the components in Lync were somewhat likely to have caused the call failures. So Score completely was unable to diagnose call failures in Lync. It had very poor recall. Pinpoint, on the other hand, thought that around 10% of the components in Lync were responsible for the call failures that we were seeing. So it had very poor accuracy. Ideally, we would want a localization algorithm to have low diagnostic rank and low diagnostic time. And so we started thinking whether one of these algorithms or some of these algorithms are better than the others. And to verify this, we actually tested these same algorithms with another system, very different system, Exchange, that is used for mail delivery. And to our surprise, this time the algorithms performed differently. Score was not only fast, it was extremely accurate. So the question that we asked was, why do different algorithms behave differently with different systems? And this is what our work is about today. So basically, the first contribution of our paper is a framework that explains why different algorithms behave differently with different systems. Now, the insights from this framework actually helped us design a fault localization algorithm, Gestalt, that works well with a variety of network systems. So as I said, there are a very large number of fault localization systems that have been proposed. They have been proposed for very different target systems. They look extremely different from each other, and it was actually very hard to compare one with another because there was no common ground. But through the course of our research, we found that they all fit very nicely in a 3-part framework. So all of these practical algorithms have a model that they use to figure out the system operation. Now, given this model, they are able to generate root cause hypotheses for the failures observed, and for this, they use something that we call a state space explorer. Then, after they generate all these hypotheses, they rank them based on how well they think they can explain the call failures. And for this, they use something that we call a scoring function. And I'm going to go deep into each of these with this example. So in this picture, you're seeing a client and a server. They're connected by 3 paths. One of the paths goes via router R1, and the other 2 paths go via router R2. The connectivity between client and server has failed. And so we want to figure out the failure of which of these components led to the failure in connectivity between client and server. And so a localization algorithm will first need a model that encodes system operation. So you could use a deterministic model to encode this system operation. So this model is saying that if any of the routers R1, R2, R3, and so on fail, then the connectivity between client and server is impacted. This model is simple and can be used for fast fall localization, but it has very low fidelity. If you see, if R1 fails, it thinks that the connectivity between client and server will go down. You could do better. You could use a probabilistic model. Now this starts encoding uncertain impact. So this model says if R1 is going to fail, then there's a 50% chance that the connectivity between client and server is still going to be up. This model is harder to build because you need to know the uncertainties. All right, so we have a model. Now, the localization algorithm is able to explore hypotheses and systematically for all the failures that are observed. One way to explore hypotheses is to do a combinatorial search. So the algorithm could systematically say, maybe R1 failed, maybe R2 failed, maybe the combination of R1 and R2 failed, and so on. So because it has to explore all combinations of failures, this state space explorer, the combinatorial search, can take very long. During the course of my talk, I'll be presenting another state space explorer that is iterative, that can go through simultaneous failures much more quickly, and we'll study it in depth. All right, so you generate the hypotheses, and now the localization algorithm needs to rank these hypotheses as to how likely it is that this hypothesis actually caused the failure. So the algorithm can do something like this. It can say, if R1 failed, then according to this model, the client-server connectivity is down by 50%. So the score is half, the probability is half. But if both R1 and R2 fail, then the client-server connectivity goes down with a higher probability. So a high score indicates that this hypothesis is a more likely root cause. So there are different scoring functions that algorithms use. They try to check against a set of observations that they have, or they check against all the observations that they have. They check the hypotheses along all the observations. So there are multiple choices that one can make. And we describe these choices that a localization algorithm can make in the paper. But basically, I just wanted to show you that the 3 algorithms that we chose, score, pinpoint, and Sherlock, make very different choices along these 3 dimensions. So I told you how a localization algorithm works. But there are a few system characteristics that actually confound localization, and we mentioned these in the paper. There is exactly one that I want to go through today. So let's talk about observation noise. It results from incorrectly recorded or observed transaction state. In this picture, you're seeing a call that's been set up between 2 people. It goes via voice gateways and a PSTN network. Now, all of these components have reported to the monitoring server saying that, call setup through me has succeeded. And so the monitoring server thinks everything is hunky-dory, the call has succeeded. But there is an unlogged error in the voice gateway that has led to the call failure. And so the call has actually failed, but the monitoring server thinks that the call has succeeded. And this provides no indication of the gateway failure. Now, noise can go the other way around too. Because of logging errors, you may think that successful transaction has actually failed. Now, The design choices do very differently with observation, perform very differently with observation noise. Some of them are robust to observation noise, some of them are not. I've just put in this table here to tell you that there's this table in the paper that explains how different design choices do with each of these confounding characteristics. The reason this is important is because this study actually helped us explain previously unexplained behavior in certain algorithms. Now, the paper max coverage had said that score seems to be sensitive to noise, and we were able to pinpoint exactly why score is sensitive to noise. I'm going to be explaining that result soon. Okay, so I want to concentrate on two results today. And this helped us design Gestalt. The main result is greedy set cover as a state space explorer is extremely sensitive to noise. But without noise, it can diagnose simultaneous failures very well, very quickly, as compared to combinatorial search that takes a very long time to diagnose simultaneous failures but is very robust to noise. So I told you all of these points. Greedy set cover is an iterative state space explorer. It helps detect simultaneous failures much faster than combinatorial search, and it works well in the absence of noise. I'm going to show you how greedy set cover works with this example. So I have two clients, client 1 and client 2, connected to server 1 and server 2. And there is a model that captures these paths. So the model is telling us client 1 is connected to server 1 using paths through R1 and R3, and so on. So the connectivity between these clients and servers is monitored. We have the following observations about this network. We have two observations that say the connectivity between client 1 and server 1 is down. We have another that says the connectivity between client 1 and server 2 is down. And we have an observation which says the orange path is up and working. And I've constructed this example, and I need the localization algorithm to detect that R1 and R2 have failed. And we will see how greedy set cover comes up with this hypothesis. Okay, the way greedy set cover works is that it selects single component failure that explains most observations in each iteration and adds it to the hypotheses. It stops when there are no more observations that can be explained. This table is showing you the set of single component failures that greedy set cover will explore. Maybe R1 failed, maybe R2 failed, or maybe R3 failed. Let's concentrate on the failure of R1. Now, as soon as you say maybe R1 failed, we can immediately explain the first two observations, which say client connectivity between client 1 and server 1 is down. Of course, R1 is down. It in fact actually explains the fourth observation also. The reason why the connectivity between client 2 and server 1 is up is that while R1 has failed, it was never used in that path. It unfortunately does not explain this observation that the connectivity between client 1 and server 2 has failed because R1 was never used in that path, and still that connectivity has failed. Still, the failure of R1 can explain 3 observations out of 4 and is the best that we can do right now. So greedy set cover says, I select R1 in my first iteration. My hypothesis says that R1 might have failed. Then greedy set cover tries to explain the remaining observation. And we can see that the failure of R2 nicely explains the remaining observation. And so the hypothesis that greedy set cover comes up with is that the simultaneous failure of R1 and R2 explains all observations. So I'm going to present this as my hypothesis to the localization algorithm. So greedy set cover has succeeded. Let's introduce some noise. So we introduce noise in one of the observations, and we say, maybe the monitoring engine thinks that the connectivity between client 2 and server 1 has failed. Now things become different. Now the failure of R3 explains all of the 3 of the observations. And so greedy set cover says, I'll select R3 in the first iteration. And then it proceeds to select R2 in the second iteration for explaining the remaining failure observation. And so greedy set cover completely ignores the failure of R1 and comes up with a hypothesis that maybe R3 and R2 together have failed. And that's the only hypothesis that it presents. So it has completely missed one failure. So this is how greedy set cover is sensitive to noise. And basically, we wanted to do better in Gestalt. We wanted to have an iterative state space explorer because it's fast. We didn't want to do combinatorial search, but we wanted to handle the sensitivity to noise. And so using this insight, we came up with this iterative state space explorer that does the following. If n is the fraction of observations affected by noise and O is the number of observations, then we cut some slack and expect the real culprit will explain n by O fewer observations. So here, 1/4 of the observations are affected by noise. And so our state space explorer says, while R3 does explain the maximum set of observations, R1 actually explains sufficient number of observations, given that we will have 1/4 of the observations affected by noise. So we actually select both R3 and R1 because they explain sufficient number of observations in the face of noise. We already know if you follow the path through R3, in the second iteration, we'll choose R2. Now let me work out the path with hypotheses as R1. In the first iteration, we choose R1, and in the second iteration, we choose the failure of R2 and R3 because they explain the rest of the observations. So our state space explorer actually presents 3 different hypotheses to the localization algorithm. It says, maybe R3 and R2 fail simultaneously, but there is a possibility that R1 and R2 have failed simultaneously. And that is how we're able to have better recall. In fact, Lync has 10% observation noise. The real Lync system has 10% observation noise. And Gestalt was not only able to use the state space explorer and diagnose faults accurately, but also very fast. We have results in the paper that show how Gestalt performs with other systems, Exchange and Abilene. And in all of these, Gestalt has high accuracy and low diagnostic time. That brings me to the end of my presentation. Today, I gave you a glimpse of a framework that explains why different algorithms behave differently for different systems. And I also gave you a glimpse of how we designed Gestalt, a fault localization algorithm that can work with a variety of systems. Thank you. Questions?
Hi, good morning.
Hi.
Steve Muir from Comcast. This is very interesting. This is good work. It seems like obviously the observation noise parameter is key.
There are a set of 5 confounding characteristics that we present. I just chose observation noise because I could make the 17 minutes.
But so in that particular case, though, is that something that you just kind of gather that you determine that value by, looking at all the data that you have, or is there some other way of sort of predicting when it will be high, when it will be low, if in fact you came at a reasonable value for it?
Yeah, so the way you do this is you have a history of the failures. So we had a history of call failures that were diagnosed manually, and then we had figured out what had actually failed. Then we looked at this historical data, fitted it back in our model, and said, okay, how do the observations look given these failures? And then we compared it with the actual, how the observations actually looked, right? And if you'd see the difference, you'll be able to come up with this percentage value of noise.
Is that something that can be automated, or is that, it sounds like that's quite...
Yes, you can. So you just keep gathering your historical data, you look at your model, keep building, making your model better, and then comparing it, and then you will say, okay, this is the amount of noise that I estimate is there. Yeah.
Okay, thank you.
Thanks. Okay. Thank you so much.